All right, we'll move on to our next speaker, who is Dr. Julie Robinson. She is the Chief Scientist of the International Space Station. She represents all ISS research disciplines at the highest level in the program and provides information and recommendations to senior leaders inside the agency and stakeholders outside the agency. She chairs the ISS Program Science Forum, made up of the senior scientists from each of the primary space agencies, comprising the Space Station International Partnership. She is also currently the acting chief scientist for Johnson Space Center. Her doctorate is in ecology, evolution, and conservation biology, and in her own work, she's collaborated with scientists to increase access and use of NASA data in remote sensing applications. Julie.
Thank you so much. It's great to be with you here today, and in a very short period of time, I'm going to take you on kind of a whiplash tour of some of the science accomplishments, some of the things that you may or may not have heard about. One of the things about the research on the space station is it covers so many different disciplines that any of us who are working in our own discipline will often be unaware of the things going on in different disciplines, and in that way, it's a very unique laboratory. Now, as you heard Ellen mention earlier today, one of the unique things about the space station is it's been declared a U.S. national laboratory back in 2005. The Center for the Advancement of Science and Space began to manage that laboratory in 2011. And what that means is that NASA is not the single point of entry for research in space. In fact, anyone who has raised the funding through National Science Foundation, National Institutes of Health, through commercial R&D efforts, has the ability to take that research to the space station. I want to talk a little bit, because that's such a different concept, and many times our academic colleagues really struggle with that because they imagine NASA as being the controller of science in space, and this was a really substantial shift. And one way of explaining that is taking a single discipline, such as the case of biology, and showing how basic and applied research intersect in that structure of ISS as a national lab. So you see down in the green dot on this chart, at the intersection of fundamental research, we have things like NASA's space biology program, but also research funded by the National Science Foundation. And in that area, in that part of the curve of fundamental research, the CASIS aspect of research and the NASA research mission can look fairly similar. But as NASA moves out towards translational medicine, taking care of the astronauts, ensuring they can be healthy on a trip to Mars, and then eventually moves that knowledge into flight medicine, you have a curve or a transition from fundamental to translational to clinical application of the results. In the same way, down here on Earth, you have a transition of fundamental research to translational research to clinical use of that knowledge for healthcare here on Earth. And many times those are intersecting the same physiological disciplines or the same kinds of knowledge, and yet their application is very different. And so because of that, we see these great examples of synergies where national lab research crosses over to become with a new idea that then is funded by NASA, and vice versa, where something that NASA funded early on then becomes a national lab piece of research. And many of our most brilliant academic scientists are working both sides of this curve and bringing their great ideas to space, sometimes with NASA funding and sometimes with other funding. So on the ISS today, we really are addressing almost the full breadth of scientific endeavor. And here I've divided the major disciplines between National Lab and NASA, just to give you a sense of that biology and biotechnology is really pretty much split 50-50. Human research is still primarily being done by NASA, but there are a number of collaborations coming up in the works where National Lab users will be using data from human subjects. Physical sciences is split about 50-50. There are a number of technology demonstrations, even though we often think of that as something primarily driven by NASA exploration missions. There are a number of cases where those tech demos are done by aerospace companies that are going to apply them to other kinds of business opportunities. Earth science, space science, and then the National Laboratory really drives the education endeavors on ISS today. So I want to give you a whirlwind tour. I'll pick 5 examples, and one of them, because Dr. Ting's here on the panel, I won't need to go into with you at all. An incomplete and biased list of what I see as some of the compelling results recently, just to give you a sense of that breadth. The first is in cell biology. So for the first time, something that people often believed has been shown, which is that mechanical unloading of stem cells affects and inhibits their differentiation. So their stemness stays the same for a longer period in microgravity. And of course, not only that, but it's identifying which genes are active in maintaining the stem cell nature and how that affects embryological development. I see that as a really significant new publication. Also, the observation of the way that osteoblasts and osteoclasts, those are the cells that control bone remodeling and bone formation, the way that those are changed by being in a microgravity environment. And in this case, the work was done in fish, in a transparent form of Medaka, where the activity of those cells could actually be imaged using green fluorescent protein in living fish. And so what you see here are some pictures of the live imaging of those animals as the scientists understand which genes are turned on in regulating the osteoblast and osteoclast activity. Another important recent result is understanding what is happening to the human immune system in producing cytokines in space. And this is important because we know that astronauts show signs of immune dysregulation. Their white blood cell, their leukocyte, their lymphocyte, and their T cell counts are unchanged. But if you challenge those cells to actually respond to an immune challenge, they don't produce cytokines the way that we would expect them to do so. However, crew members also don't get sick. And so this is a really interesting window into that black box that is immune function in human beings. If you look across a number of the medical challenges that face us today, having the immune system respond properly when it needs to and not respond when it doesn't need to is really one of the great medical challenges that we're facing. And so the work on the space station helps us make sure that we're going to keep our crew safe as they go in isolated environments further and further from Earth, but it also provides this unique insight. The cool flames phenomenon was discovered in some of our combustion experiments on the space station. What this phenomenon is normally when we do combustion on the space station, and we're burning something almost every day, people don't realize how many times we're burning things up there on purpose and safely. Normally those combustion events happen at about 1400 degrees Fahrenheit, and scientists can control the flow rates, the different gases, the different fuels and conditions. What scientists discovered is that in microgravity conditions, rather than just simply suffocating itself, under certain conditions the flames could reignite, and that those flames were then burning at about 600 degrees Fahrenheit, which to a combustion scientist is cool. Now to me, a biologist, that sounds pretty hot as well. But what it means is there was an inefficiency to that combustion that could be exploited by understanding the physics underlying that. And we've had a number of follow-on experiments being done on the space station and continuing today to better capture and understand that overall process. I'm not going to scoop Dr. Ting's results since he's on this panel, but I just cannot put a chart up about science highlights from the space station without putting an AMS chart in there. Just to make sure that you recognize that the work that he is doing with alpha magnetic spectrometer to understand the nature of dark matter and dark energy in the universe is fundamental to our knowledge of science as a whole and a really important discipline as well. So not only do we look at the science discoveries, and I just told you, especially more for the scientists in the room, some of what those discoveries are and why I think they're important. But at NASA, we're expected to do more than that. We can't just do, and I think this is true for all of us as scientists, we can't just do something because it's interesting and because it provides new knowledge, but we have to start thinking about the benefits that come back to society from the work that we do. And we track those for our International Space Station research, the over 2,000 investigations that have been done so far. And we see emerging benefits for people here on Earth in really 5 major areas. One is in the area of human health. One is in Earth observation, disaster response, and remote sensing. Also in technologies that change lives and make things better here on Earth. In educating and inspiring young people to seek careers in science, engineering, technology, and math. And in the development of commerce and commercial models themselves. And just a couple examples of some of the benefits that we're tracking. One is the development of a 2-dimensional nanofiber layer that can mark the surface of a semiconductor, so something useful to a number of industries here in Texas. Also, there are clinical trials going on for a new drug for treating Duchenne's muscular dystrophy. This was developed by our Japanese colleagues using protein crystal growth on the space station, and they're in their second phase of clinical trials so far. The first genetic results that investigate a link between folate and eye health in space. Some of you may know that our astronauts have, at least a large portion of our astronauts have vision impacts from being in space, but certainly not all of them, and understanding what genes are associated with that and what other factors could introduce that risk is important for us for exploration, but also provides a window into a very different process that we don't know anything like this on Earth. The constrained vapor bubble experiment has helped us understand the effects of Marangoni convention inside heat pipes. Now, if you think you don't care about heat pipes, touch your computer, because that's how a number of components in your computer and in other small electronic devices are being cooled. And so if you can increase the efficiency of that by better addressing the physics of the way that heat pipe is working, there's the possibility of miniaturizing and being able to cool larger chips in smaller devices. So really significant potential impacts of that work. And measuring of the capillary flows in space has allowed us to get fundamental equations that are then being applied in developing better lab-on-a-chip technologies. One example of that is the human emulation system, but there are a number that are taking those equations and finding benefits and products that those can enhance here on Earth. So that gives you a sense of both the sort of fundamental discoveries as well as how those things begin to make their way into the technologies that affect our lives every day, affect our health every day. As we look out towards 2018, I wanted to give you a sense of what I see ahead for science on the space station. First of all, we're really excited about the first publication that we expect in the spring of 2018 from our twin study. This is the first time that comprehensive genetic studies have been done of astronauts. We looked at Scott Kelly as our one-year mission astronaut, but also at his brother Mark as a sort of a ground control. He's an identical twin. And this gave us a window into doing something that really people would not have asked astronauts to do themselves because of the Genetic Information Non-Disclosure Act and the difficulties with privacy. But it was something that Mark and Scott were willing to do and has allowed us to begin to look at all of the different genetic effects of being in space and how that works on the human as a system. This is definitely one subject. We'll have more studies coming down the pipe in the future, and having these first publications come out this year is, I think, really something to watch for. Another thing to watch for in the coming year is the launch of the Cold Atom Laboratory. This will be essentially the coldest spot in the known universe, about a billionth of a degree above absolute zero, and it will be able to create a Bose-Einstein condensate that can survive for about 5 to 10 seconds. That provides the ability to do fundamental physics work in an absolutely unique way that can't be done here on Earth, and really opens up the opportunity. We have several Nobel Prize winners that are some of the first investigators involved in the study, and science teams lining up to use this facility over the next few years. So I gave you just a rapid fire, and I shifted from discipline to discipline. So if you're used to hearing 15 minutes all about one discipline, that can be a little bit uncomfortable. What I want you to realize is that the access to the space station is more open than it has ever been before. And in fact, you don't have to have your whole lab tooled to use the space station and 23 people that know how NASA works to do NASA paperwork to do things in space anymore. So if you haven't had a grad student or a postdoc take a look at taking one of your experiments and bringing them to the space station as a quick turnaround through the National Lab, you really need to do that. There are folks from engineering at A&M that we meet with on a regular basis, folks from UT. There are individual labs out there doing it, but I'm often surprised at how little Texas universities take advantage of how close they are to Houston in taking advantage of the National Lab. And CASIS has offices here. They work in this ecosystem to help work on commercial ideas. Also, the National Institutes of Health and the National Science Foundation all have programs where you're funding there. Even if you aren't funded by them to do something in space, many times you can find a way to leverage that funding and get access to do a preliminary experiment in space, and then that can open up greater opportunities. To find out more about that, you can go to our ISS Research and Technology online site. You can also go to iss-cases.org and read about how the National Laboratory works. You can follow us on Twitter at ISS_research, where we really keep you up to date on what's going on. And you can even download our app and see what other people have done in your discipline. Search by keywords, find out what's going on in that area, and see if there might be something that you're interested in as well. Thank you very much.
Thank you, Julie. So please, again, if you can step up to a mic if you have a question. It's really hard to see here, so. Well, I have a question a couple of questions maybe. So as you talk with scientists, you know, when we started to build the space station, we tried to see what it would need to do to accommodate science. But knowing what we know today, are there different capabilities or attributes of a space station, a space laboratory that we would add now or do a little bit differently based on what we've learned over the years?
Well, certainly, tried to have early in the space station central for a large number of rodents. And that was something that was designed to be so large that its own for us to continue some of the rodent research with centrifugation at the
I don't think these are working. I'm hoping they didn't turn off your mic.
Try to talk loud. Maybe that will work better.
Number has on our other to add more rodent capability.
And our Japanese colleagues have now built a small rodent centrifuge. We have a queue of people wanting to use those facilities, and I think, honestly, we're finding that the demand for those facilities are exactly what we imagined it would be ahead of time, but the engineering couldn't provide that big module. So we're gradually, in an incremental way, replacing some of that capability and providing the breakthroughs that the scientists need.
Thanks, and I think I see a couple people back here, so please go ahead.
Yeah, so there has been some limited research done on cancer cells. There are a number of experiments in the queue being developed and planned to go to ISS, and there are a number of new facilities coming online that are built by different commercial partners, where they basically help the user to take a culture from their lab and don't have to learn about that hardware. They can just get a lot of help in then flying a culture in space. And so I think we're at the point where we're going to see a tip in a better understanding of how cancer cells respond. It's a great question, because if you see things like changes in differentiation, the immediate thing you think about is, well, would that affect the way that tumors grow? Some of the preliminary data suggests that some tumors may look more like tumors that grow inside the body than normally they would look in culture. And that would provide a real opportunity. And it has to do with probably with the fluid shear forces and the way that capillarization forms in the body. So there's really a potential there, but it's definitely untapped. We're at an investigational or a discovery phase in that area.
And I would also say there's been a number of experiments where they don't necessarily have cancer cells, but they're related to cancer treatment. For example, drug delivery and how you might do that with microcapsules or drug-antibody pairs. So a variety of things that can be applied to cancer research as well. Another question?
Right, that's a great question. And in fact, if you want to I can get a little excitement in my life if I go to the right hallway at JSC and toss out that question, because I can get the scientists to have a great argument about that even today. There are kind of two schools of thinking right now. One possibility is that the ISS is so clean that because we have HEPA filtration, we have charcoal filtration, the crew members are quarantined before they launch. We don't let them kiss their children. And so they get up there and have a pretty clean environment, and they don't bring a lot with them, so that their immune system isn't challenged. And if your immune system isn't challenged, standing down and relaxing is probably okay. So one possibility is it's adaptive and it's temporary. Another possibility is that you're really seeing a fundamental inability of certain cells in the immune system to differentiate and respond to an immune challenge, and that is the other point of view. That's supported by some of the culture studies, for example, some of the T-cell activation studies that have been done in culture. And we really have to do additional work to keep understanding which of those two possibilities is the right one, or maybe the truth is somewhere in between, which seems to usually happen when scientists are disagreeing.